Hello, everyone. Welcome to our panel. I think we have a slide here, an introductory slide. We're going to be talking about AI and VLSI, a symbiotic revolution. And this has been a common theme throughout this conference over the last couple days, and we're going to dig a little deeper into it. And so I'll introduce myself. I'm Ramuni Nagaseti. I'm with NatCast, which is the National Center for the Advancement of Semiconductor Technology. And prior to that, I was with Intel for 29 years. And the way this panel will work is we're going to start by each one of the panelists giving a 3-minute introduction to themselves. And then we're going to dig into some prepared questions. And if we have some time left, we'll also go into some ad hoc questions from the audience. And so with that, I'm going to let you start, Arijit.
Thank you. Thanks, Ramuni. My name is Arijit Ray Chaudhary. I am a professor in Georgia Tech. I am also the school chair of electrical and computer engineering. My research areas are mostly in the area of design, circuit design. So I've been a happy benefactor of the EDA industry, although I've never been in the EDA industry. In the past, I have worked at Intel for about 6 years in the circuit labs, mostly as a digital mixed signal person, as a researcher. And before that, I used to work at Texas Instruments for a couple of years, working on analog design. So I have kind of done more of the design kind of work in the last almost 20 years of my career. My first DAC was in 2003, when I was a student, a first-year student, a grad student. And this is the 22nd year that I'm coming back to DAC. I've missed a few years in the middle, and it's always great to be here. And thanks for the invitation to be on the panel.
Okay, that's great. I want to say we have another slide. There we go. Thank you so much. Okay, we'll go ahead. And next is Rob Aiken.
Yeah, hi, I'm Rob Aiken. I am currently a program manager with the National Advanced Packaging Manufacturing Program. I am not here as a spokesperson in any shape, way, or form for the U.S. government. If you take a Venn diagram of people authorized to speak for the U.S. government and me, it looks like that. My usefulness perhaps on this panel is I was at Synopsys previously, and then ARM research for a long time working on some of these types of problems. Prior to that, I was at a few places, but one of the first jobs I had was actually doing internal EDA at HP, so that was a long time ago. I was trying to remember when my first DAC was. The first DAC that I came to here was 1991, but I think that was maybe the first one.
Wow. Yep. All right, go ahead, Sydney.
I'm Sydney Tai. I'm from IBM Research down here in the Bay at Almaden. And at IBM, we do design for AI and also AI for design. On the design side, we design AI accelerators, including like systolic array, near memory, in-memory computing. That's my main research. We also do a lot of AI. And the AI space, we focus on AI for manufacturing and large language model for design. And so manufacturing is like using our data from IBM Albany Research Center. So we try to do like defect root cause analysis. And on the LLM side, we have explored a lot of application because the hype is there. So we, for example, we have an Ask EDA chatbot, like every company has now. And also we have a documentation effort to go from RTL directly to documentation because no designers want to do documentation. These are the safer application, we think, because the output doesn't go into the design, but it goes to the designer. We also try to generate designs like RTL generation because code generation is a very good use case for LLM. But the requirement for error is very, very low, so no tolerance for error. So we also work on verification and try to do synthetic data sets and so on. And last but not the least, we also do analog design. There's more exploratory. We try to have the LLM generate some topology. And there, of course, we need to combine with reinforcement learning to actually make sure it goes in the right direction. But I'm very happy for the invitation and look forward to the discussion.
Manoj?
Hey, folks, I'm Manoj. I'm with Intel. I'm responsible for product enablement, which is CAD flows, EDA tools, technologies, capabilities, and all of that. I've been in Intel for about 20 years. I started in architecture, spent some time on design and validation, and now I'm part of the enablement team. Obviously, as part of enablement, AI plays a massive role in changing the way we work, right? Changing the way we work, my team work, was also the way Intel designs chips, Intel designs products. So quite excited to be part of this conversation, and looking forward to kind of discussing the impact of AI all the way from architecture to system to design to physical design, right?
Fantastic. So the first question I have for you is that it seems that AI in chip design can be used at many different stages. It can be used up front with RTL, in the back end with floor planning and place and route, and in validation and debug. And so I'd like to know, where in the design flow is AI being used most effectively, and maybe in contrast, where it might be the least effective? So do any of you have an answer there? Manoj?
Sure, I can jump in. So I think, as Sydney said, the first place where I think we've all been successful deploying it is with knowledge assistants, right? Chatbots and knowledge assistants, I think a fairly easy market, low barrier to entry. So I think we all have chatbots that help you understand documentation, that create documentation, that parse through dozens and dozens, thousands of log files and get you the information that you need. I think this is very successful, and I think it's fairly well deployed. I think in verification and test areas, the concept of compaction of tests, I think, is something that's a fairly, navigated space. There are good tools, good solutions where instead of running 1 billion cycles to find a bug, you're now able to go run 1 million cycle, 100,000 cycles to find a bug. In terms of tester time, be able to compact tests, I think that's a solved problem. And I think in physical design, the concept of design space optimization and kind of exploration of design space, again, is a fairly well, I think, tackled problem, especially by the EDA industry. So I think those are 3 areas that I think we've made good progress in terms of deploying solutions. What I think we have not yet got into, and what is kind of the next inflection point, is how do you do cross-stage optimization? I think today, most of the deployments that we've had is within a particular stage. You look at verification, you look at physical design, you look at code generation. I think deploying solutions within a stage, I think we've done a fairly good job, and I think there's a lot of investment in it. But to me, really, the big breakthrough comes when you're able to take insights from sign-off and pull it back to APR, and take insights from APR and go back to your logic design, and take insights from post-silicon and go back and change the way you do verification DV in front end. So I think those types of cross-stage optimizations, I don't think we've cracked yet, and I think that's what's in front of us.
Thank you. Would any of you like to add anything to that, or?
Maybe just a piece of historical context, because if you look at AI and EDA, AI optimizers of various sorts have been in EDA tools for close to 30 years. And AI adjacent even genetic algorithms are sort of AI adjacent. And all of this stuff has been buried in optimizers inside of tools invisible to the people running them. So you run the tool, do you know if the optimizer is numeric or AI or heuristic driven or whatever? All those things are buried. The first real use in ARM for AI was actually related in verification pattern generation. And it came around right around the time of ImageNet, when people looked and said, you know what? If you make pictures out of test patterns, you can use image recognition to look for particular classes of images, which are particularly successful test patterns. So that type of a process went. And so again, I think there's a long history of AI of various sorts inside of EDA. And there's, as Manoj pointed out, there's tons of opportunities ahead too. So.
Fantastic. Any other perspectives to add, or should I move on to the next question? All right, so the next question is actually a bit related, because my background is in process technology and device physics, and so I think of things all the way from process definition all the way through execution. And so the question here is, where in the process technology and design lifecycle is AI being used effectively? For example, in process definition or DTCO, standard cell library architecture, design concept exploration, design execution, post-silicon. So kind of the broader space beyond just the execution of the chip design. Where do we find AI being most widely used and successful? Arijit, sounds like you nodded.
All right. I can give you my perspective coming from the academic setting, looking at what the researchers are kind of working on and what are some of our collaborations with the industry are kind of teaching us. So one area where I see a lot of interest is essentially AI-assisted materials discovery. So there's a lot of interesting work going on in that space where optimizations and kind of understanding processes and materials discovery. This has, again, been going on for almost 10 years now. I think I'm seeing a lot more work because there's a lot of data available. So I think there's a lot of interesting things going on at that space. The other place where I see a lot of very interesting work coming out is essentially creating digital twins, like digital twins for processes. And these are physical processes. So you're trying to essentially create almost an identical digital virtual version of that. It's not only a great tool for research and for actual implementation in the industry, it's also a great opportunity for us for education. So that's the part which is kind of very interesting, because once you create digital twins of processes for manufacturing or whatever that might be, it gives us an opportunity to kind of teach students on how to work on a virtual machine without actually touching the machine. So it's a great way of democratizing research and education in that space as well.
Fantastic. Sydney?
Yeah. So I would say, like Rob said, AI has been in the field for a long time. And the difference now is the boom of deep neural network and also the language model, the different type of model. And that suddenly provided us a lot more compute and more tools to analyze our data. For example, now we can easily do all kinds of classification tasks like time series prediction. And so the same big data that we used to have, or even now the tools generate even more data, we are able to do more AI on it and try to optimize like from the defect, the process, and do a lot more optimization in terms of is this a design problem, or should we fix the design rule, or is the tool process that you should change the recipe. So I feel that there's a lot more opportunity, and people are like applying new tools to the old problem and like discovering amazing things. And we also do material discovery, so we can talk more about it.
All right. Any other answers for that question? We'll move on to the next question. All right, so the next question is about software-hardware co-design. And so I think this kind of like feeds off of something that Rob said about cross-stage optimization. So that boundary between hardware and software would be one of those stages. And so do you think that AI tools are going to kind of reinvent or reshape this concept of software-hardware co-design?
I think so. I think all the way from being able to kind of architect your system, when I think of a function that I need to do, what goes in my hardware, what goes in my firmware, what goes in my software stack. I think that architecture exploration, I think there are tons of opportunities for us to kind of explore the space and identify the right sweet spot in terms of power, performance, area, but also in terms of sort of on-field fixability of things, right? So I think there's a lot of tools now that can help with that exploration of this space, but then follow that through with, as you design, be able to debug. I think one of the big challenges today is be able to do hardware firmware debug. You look at a typical laptop or a desktop, you have 25, 30 microcontrollers with firmwares running on them and a system stack running on it and drivers running on it. And when you have a bug, when you're trying to go debug a bug, it could be anywhere in your RTL, it could be in firmware, it could be in your driver stack, it could be in your software stack. And I think the verification space, the hardware-software co-verification space, I think is just exploding, right? And I think this now has gotten beyond the ability of an expert validator saying, I think the problem is going to be there, let me go look, right? And I think having AI help with sort of locating the problem and saying, look here, based on thousands and thousands of bugs that I've seen, hundreds and thousands of runs that I've seen, I think that also helps significantly with sort of the hardware-software co-design problem statement. And of course, on the field, when you have to go optimize things, you take power management. On the field, based on the workloads, based on the use cases, I'm learning what the usage is, so I'm changing my algorithms of my power management firmware to on the fly give you a better experience. I think it also helps how you design stuff, because you know that on the field I can do a lot of intelligent stuff, and that changes the way you're architecting things, right? So I think across the board it makes a big difference.
I think there's a lot of opportunities in it as well in sort of domain specific or accelerators of various kinds, where historically the challenge has been, I can build an accelerator that's super cool and wonderful, but no one knows how to program it. But if you can co-develop the programming aspect of it, so the compilers and the drivers and the rest of all that stack, if you can co-develop that and the hardware that implements it, that's, I think, an opportunity that has the potential to greatly simplify how such accelerators come into being and how they can connect to the rest of the world. So,
and lower the barrier to adoption.
yeah, exactly. And so I think, again, there are a lot of possibilities that can go on there. There's also, I mean, we've seen, you can look around this floor, there's lots of people who are looking at how do you make hardware design look more like software design? And there's again plenty of opportunities with large language models that have been trained on effectively an infinite supply of software and a very tiny amount of hardware. So how do you take advantage of that to do something is an interesting question.
That's right. Anything else to add on that question? I want to actually build on this access to high quality training data, especially in the hardware design space. It seems like it might be a roadblock for the use of AI in design. And so I wanted to get your perspective on, a lot of this data resides in large chip design companies and it's not widely available. And so if you could comment about the access to training data and also the potential use of synthetic data as an alternative to real world data for training.
Yeah, we talked about this when we were doing the prep meeting, and high quality data is really challenging because especially like the last panel here also mentioned that when the tool or the code is technology specific, it's even harder. You don't have access to the technology, you're not even allowed to disclose like the timing information from a certain PDK. It becomes very hard to even within the company, you want to go from this node to that node, and it may not be the same, and you have the code needs to be written differently. And so we do explore synthetic data generation, but it will be based on a certain set, and then you try to generate code that's similar, and then you try to verify that this is a good set so that you have enough training data to train your model. But I think the barrier from company to company, because it's everyone's crown jewel, is still quite high. And often at this conference, you will hear a call for open sourcing and more generic tools and RTL. So I think even the RTL can be quite technology dependent. So I think that definitely is a challenge.
Anybody want to add anything or add synthetic data to this mix?
Yeah, from an academic perspective, like an academic research perspective, having access to data is going to be super important because we have seen that in the pure, let's say computer vision space, where a lot of the advances in AI, particularly coming from academic research or research labs, has been has dependent on the availability of image data, for example. I think in the AD industry, or particularly for design, at the moment there is nothing which is open source that we can use that that can help us with academic research. There are all these fragmented efforts at the moment. But I feel like this is something as a community we will get together between the industrial academic partners, and maybe the government can help and allow people to kind of have more open source. I don't know, competitions maybe that the software industry has done. Essentially, we need more data to be able to kind of make any advances. Otherwise, what ends up happening is the academic research at least in my area, which is design, has so far been at the same level of, I'd say, complexity as industrial research, but we are going to start falling behind very soon if this is the vector that the industry wants to pursue and we don't have data. So I think this is a critical need for the overall ecosystem at the moment.
Would synthetic data help fill that gap, or is it not?
Yeah, I think so. So again, this is at a very personal experience, drawing from that. Synthetic data is useful as long as it mimics the real world. I think a lot of synthetic data is just data. It doesn't represent anything. So I think being the industry kind of validating that some of the synthetic data is useful would be important. So I think if you have synthetic data that's generated by a tool, we have to, I think that's where we need expertise to be able to say that synthetic data is actually meaningful data. Otherwise, if you teach a tool, from the corpus of incorrect data, then it ends up becoming a self-fulfilling kind of thing. And then it leads you down a rabbit hole. So I think that's something which I'm a little skeptical about in synthetic data. I think it needs to be properly vetted by big companies, experts, and so on.
I think along with it, the algorithms also are evolving and will evolve to be able to deal with layers of information security management, right? We should be able to do layers of training, layers of learning, where I'm able to contain my information and be protected with stuff that I need to protect. And I think the algorithms will evolve to get there, right, as well.
I think there's also a way of coming at this problem where rather than saying, oh, we don't have enough data, panic, 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 we have plenty of data in other places. How can we take the data that we have and apply it in these situations where we have less data? So to me, that seems like it's at least as good an approach as using synthetic data. So.
Thank you. So another question related to these different techniques. Can you comment about reinforcement learning in particular, if that has a particular place in this whole chip design in the scheme, or if it's like widely applied or narrowly applied? I've seen it mostly applied to place and route.
Yeah, I think place and route was a very successful example from Google and Stanford, and we also try to use it for analog design. And I think reinforcement learning is a tool. When you have the ground truth or a score, you can apply that to guide the exploration process. And so I think it is a good way to inject expert knowledge and like tool results. So I think it's one of a very powerful tool.
All right. So I want to talk about 3D IC design now, because that's where we're having a complexity explosion. And so I'd like to understand if AI techniques are kind of a prerequisite to being able to do efficient 3D IC design, or so like an enabler to actually help this inflection point move forward in terms of the 3D IC era. Is anybody thinking about 3D IC?
I can comment more from the 3D IC for AI accelerator perspective. From the design and tooling perspective, I feel that we are in the early stage for 3D IC. There's a lot of potential. The technology is still rapidly evolving, different type of bonding methodology. And the cross-chip design is primarily right now manual but division of the chip is more manual, and also the floor planning is kind of separate. And so I would say right now it is still more focused on the technology development stage. It is not a prerequisite that you have exquisite AI to enter this field. It's more like you need to have the exquisite technology to be able to design and yield the design. But I do think that some more system level optimization definitely helps in the 3D space. So with the complexity of the problem, and when the technology matures a bit more, I think it will be very helpful to have 3D IC design.
Yeah, I think there's also, it's not necessarily an AI problem as much as an abstraction problem. If you look at how you do 2D design right now, you can't do 50 billion transistor flat, right? You have to do some kind of hierarchy for it. And if you then say, okay, I want to stack 2 of these or 3 of these together, you still can't do that flat, right? So you need to find an abstraction that allows you to do this optimization up and down your stack or across your 2.5D design. You need to find an abstraction that allows you to do that in a way that doesn't require you to simultaneously hold all 50 billion transistors on each dielet together. And there are a variety of ways that you can go about doing that, but it's, I think, more important, it's useful to take advantage of the fact that a chiplet boundary is a natural hierarchy point. Whereas if you have a placed and route design, even the physical blocks that you use for routing aren't necessarily the ideal hierarchy for every aspect of your design. And so there isn't really a standardized place where you can abstract out a existing flat design. So, but the fact that this chiplet forms a boundary and that the package forms a system is, I think, an opportunity that we can exploit via AI or conventional EDA means.
Thank you. Anything else on 3D IC, or move on to the next
So I think the part which is kind of very interesting as kind of following what's going on in the research space in this area, I feel like many of the AI tools, which are quote unquote optimization tools, are also allowing us to do a better job of design space exploration, not only with the electronic components, but now if you put in the thermals, you look at what kind of cooling techniques you can use, what kind of energy availability do you have, what kind of workloads you are. I think the cross-tech optimization that Manoj was talking about, I think some of the AI tools and optimization techniques can allow us to kind of do more design space exploration, system level design space exploration in a more, it's a smarter way. So I think that's exciting.
All right, so one thing I'd like to talk about are the perceived risks, and maybe like perceived risks versus real risks. But what kind of guardrails do we need to start thinking about in order to manage those risks? I think we talked about IP security. That's not really the type of risk I'm talking about. I'm talking about just risks to generally having faulty chips out there in the world. And so I'd like to hear a little bit more about what kind of guardrails we need to have in place when using AI for chip design.
Maybe I'll take a verification example and kind of think through what it means, what a risk means, right? So today, when I want to run a regression suite, I make a change in my RTL, I want to run a regression suite. Instead of running 100,000 tests, my AI bot is telling me, hey, just run this 20. I've analyzed your change. Just run this 20 tests, you're going to be fine, right? So it takes a leap of faith to trust it and say, I'm just going to run my 20 and I'm going to check it in and this is going to work, right? Because it's analyzed what I need to run and it's compacted my test. It saved me hundreds of thousands of dollars of cycles that I need to run. So it's a leap of faith that you take. It's a risk that you take. But in some sense, I'll argue we've kind of gone through this with optimization algorithms. We've gone through these with solvers. We've been on this journey. So it's not a brand new concept to take these risks, right? It's we've kind of taken risks based on coverage tools and insights that we have on analytics that say it's okay to take risks. I think now the difference is the type of risks that you take are based on algorithms that are harder for you to back engineer and understand why it's recommending something. But I think as long as you have enough guardrails in terms of coverage solutions, in terms of debug solutions, then these risks are okay to take. So I think part of it is, given these leap of faiths that you do, what guardrails and what scaffolding that you need in place to be able to take them, I think that's what we need to think through. And I think verification is a really good example of type of impact that it can have as long as you have guardrails to take those risks, right?
So I'll add something as someone who deals with 18, 19-year-olds on a regular basis. I think what happens is with the internet, knowledge has been democratized a lot, right? So we don't value memorization anymore. So if I ask my first-year freshman students to find the logarithm of or find the square root of a large decimal number on pen and paper, half of them cannot do it anymore. Which I think as a society, that's okay. Maybe we can live with that. So what it has done, access to calculators, computing, internet, and all of that has democratized knowledge. At the same time, not knowledge, information. And at the same time, I feel like it has also kind of trivialized memorization. I think if I look at AI and what the students today are using AI for homeworks and this and that, I mean that's a separate discussion altogether. But I think I fear that at some point knowledge will also become democratized and trivialized. The part that makes me worried is when you trivialize knowledge and you don't have the earnest drive to actually become an expert in something, we are not going to be able to write better AI tools. AI tools are going to be just mapping whatever it has learned from the corpus, and it's not going to be good for innovation. So as someone who's kind of in the midst of this conversation about AI in education, I feel like that's a big risk. And we have to be able to use AI, but we should not trivialize knowledge and expertise in areas so that we can continue to innovate. I think that would become an important challenge for us who are in the education area.
Yeah, I agree that the people is still the most important guardrail. So we always get asked, if we have these tools, do we still need designers and verification engineers? But the reality is that if you use more of the AI generation tool, you actually need more good verification engineers, because you should always read the code that you generate, shouldn't just take it face value, because you're generating with a black box, and if you treat the output also as a black box, there's really no check if something goes wrong. And then and all the tools that will help you. It's very easy to just use it and click the button and say that, okay, it works. I think it is, as you said, it's very important to say that you need to understand, not just get the information very easily. And so I do believe that human, in the end, needs to be the final guardrail, and we need to rely on the professors to put that in the education system.
Yeah, I think it was interesting in Bill Chappell's talk yesterday. He had a bunch of examples going over time of essentially saying to the automated system, explain your reasoning. And actually, asking it that's often a good place. Oh, how is it that you came up with this? Oh, well, because I just made it up, Or, no, I have this document, and then you can check, does that document exist? So actually, the guardrails, you can install your own guardrails if you work at it. So it's like any tool out there. You can abuse tools and get them to do nasty things, or you can use them for good things. So it's the tool doesn't care one way or another. It's kind of up to the user at some level.
So in terms of our future workforce development, this is an interesting question, because it seems like with everything changing so quickly, I don't think our curricula change as quickly. And so we want to make sure everyone has the best, most recent knowledge in terms of being relevant to the workforce. We don't want people to kind of devalue expertise either. Do you see that what are you going to tell the future workforce what they need to be studying? And we still need to study everything we used to study plus more? Is that how it goes?
Yes. Yeah. I think if you think about the students who are coming in as freshman students, they are not coming in with any more knowledge than they used to come in 20 years back, right? They still have a very shaky understanding of calculus, maybe a very shaky understanding of physics, and you start there, right? So I think in freshman couple of years that you study the basics and the fundamentals and so on, and the expectation from the industry is when you guys come and hire the students is they should know design, they should also know AI, they should also know many other things. So I think the question then is, what's the role in academia? So I see a couple of trends. One is students who want to be in a particular industry, for example, and not be an engineer anywhere, like embedded in a company. A lot of the students are going for a BSMS program now. Like they see the value of being around for one more year and getting a little more expertise in one particular area, take a little more advanced classes, do hands-on projects and so on. I think that I'm seeing a very significant trend in that direction across all the universities. So the other thing that we need to do is to work, as academics, we need to work with the industry and introduce more, I'd say, more courses in the curriculum, more hands-on design experiences. I think that has been the trend. I think a lot of the US universities have maker spaces where the students can kind of build stuff. I think that whole idea of experiential learning is going to be more and more important. So I think at the later stage of the pipeline, when the students are like juniors and seniors and maybe even master students, I think there is a real need for having more hands-on experience. And that's where I think the collaboration with the industry and academia is super important. So I think a lot of the universities are kind of doing that to some extent. But remember that when we get the students, they still come in with very shaky fundamentals. And I think our job, I see, is to make sure that their fundamentals are strong. I think if they really want to do AI, they should understand math, linear algebra very well. It's not about just running tools. It's about understanding what's behind the tools. I think if you can understand that, if you can understand what those concepts are, I think ramping up on a particular tool or doing something which is like, say, use this tool X and Y together to solve a problem Z, I think you will be able to do that in a few months. But if you don't understand the fundamentals well enough, you won't be able to do it. So I think the role of academia still remains, I think, invariant. We have to make sure that the students understand the fundamentals, and whatever hands-on experience that they need, I think we need to work with the industry to be able to provide that opportunity.
I think maybe from a corporate workforce perspective, it is a massive boon, right? Because what you can do is you take a brand new engineer that comes fresh out of college, you're staring at 100 million lines of code of something that you need to work with. Previously, it would take you 6 months to a year and talking to 50 people to understand, this is how I compile it, this is what I do here, this is what this code means, it has dependencies here, here, and here. I think today, with the amount of introspection that we have on code bases, the amount of assists that we have, all the knowledge assistants that we have, people get to productivity very quickly, right? So I think it helps you kind of get past this building tribal knowledge, building sort of customized knowledge space. I think it lowers the bar for a brand new engineer to become productive in a space. And I think it also enables people to move between domains in a company, right? You are a front-end engineer, now you want to go dabble in physical design. It's not this insurmountable mountain that you have to climb. You have tools that are going to help you to go understand what you need to do and how you can get productive very quickly. So I think there's also tremendous upside in terms of training and getting sort of incomplete academic engineers to get to productive workforce engineers.
It makes me wonder, though, you talked about entry-level engineers and this being a boon for that. How about for mid-level or even, semi-retired engineers or like people of all, at any stage in their career, can they think of this as a way to kind of jumpstart into a new area?
Absolutely. I think it enables us to move to new domains, move to new areas without a massive barrier, right? So I think it definitely helps, like I said, someone in one domain to move to a different domain and get productive. I think it's a massive aid.
I think today's workforce development, a lot happens in the company because the technology evolves so fast. You may have gotten your PhD 10 years ago, and now everything is different. And so at IBM, we also internally embrace everyone, encourage everyone to embrace the new tools, but embrace it with caution. So when you get the results, you have to double check it. It's like the RAG approach. You have the ground truth. You should click on the link and check that the link actually exists. And also. And also, what I tell students of what you should learn is you should learn the ability to learn, because you should expect that when you enter the workforce 5 or 7 years later, you're going to need to learn something else. And so being able to use the tool to automate and also learn new things is very important. And even the older engineers, I think there's a lot of productivity to gain. Like even in software, the new language come up all the time. But if you know Python, I just say, go translate this to Go or something. And you can roughly still see that the code is roughly right. And so you don't need to learn all the syntax, the for loop, the brackets anymore. And so I do think that everywhere there is opportunity for productivity improvement.
I think it also emphasizes, and in fact, you were just saying that you need an intuition about stuff. So the importance of intuition is increasing. So if you have a student who doesn't know how to do a logarithm on a paper, they should at least know that the logarithm of a 10-digit number should be, not a 6-digit number. These kinds of things. So if you have an intuition about problems, then that serves as kind of a first level checkpoint on the output of the tool, so that you can say, okay, this makes no sense. Like when some map program tells me that I should drive 40 miles out of the way to get somewhere, I can say, that seems wrong, which annoys various family members that I have because they think I should follow the directions and not take them under advisement. But
You're talking about the people who end up in the mountains stranded in like 10 foot deep snowbanks. All right, so another question I have is, to do AI for chip design, it requires a lot of compute resources. At least that's what I think. And a lot of the companies that have the most compute resources, I'm thinking about cloud companies like Amazon and Google, Microsoft. They have, in my mind, virtually unlimited compute resources. And so are those companies going to end up winning this game in terms of the overall benefits of chip design efficiency and faster time to market and higher quality and better customization, because they have the resource, that compute resource that is so valuable in this space?
I think maybe first, obviously having compute, having engineers, having experts helps, right? I think the more compute that you have, the more experts that you have, obviously it makes your works easier. But I don't know that today I would think of access to compute as a constraint that is preventing people from being successful in chip design. I think if you want access to compute, people have ability to get access to compute. I think there's a way to do AI with just scaling your compute requirements linearly or even super linearly, but there's also a way to do it where you're smart about where you apply compute for AI, right? If you go back to physical design, if I want to do APR, I want to test 100 different recipes. I can kick off 100 runs in parallel and I can go check the results of these 100 runs. This is one way to do AI. But I think another way to do it is to learn from what I've done in the past. And potentially that allows me to run less cycles and focuses on what I do, and that lowers the bar for a company or a startup that has less access to compute to get in the game. So I think it's about how you do AI and how you approach problem statements rather than just having compute. I mean, compute obviously helps, but I don't know that it's at a point where it's a blocker or a critical differentiator in success of chip design.
Yeah, I think the trend that we're putting EDA on the cloud is actually democratizing. You don't need to own the machine. You can still access, and the Google, the Amazon, as they use their cloud for their own design, they also try to sell the access compute to other people. And that makes the EDA tool also more cloud agnostic and also more portable. And you can just use it for the time you need. So it's still very expensive, and compute definitely helps. So you should use it smartly. But I do think that the trend of going to cloud and the fact that many of these companies are cloud companies actually is synergistic and may help the larger ecosystem.
Okay.
And the cloud companies are motivated to make sure that you have easy access to compute, right? That's their primary path to revenue. So I'm sure if I think it becomes a problem, it will just get more democratized and the problem will get solved.
So we have a few minutes left, and I want to open up for questions from the audience. There's a microphone right there, and I know there's probably some people who have questions.
Is it working? Is it working?
Yes.
All right. So I heard there's an overall consensus here that AI is good for us. Everyone's talking about the benefits of AI. Can you guys actually comment to, where is it detrimental? There's one thing, maybe, there's this aspect of it perhaps killing our learning abilities. But even beyond that, what is it doing to the environment? Did we come into this really quickly? I know VLSI behind this has enabled us to get to where we are, but has it happened too rapidly, and have we as a human race done some damage?
Yes, I work on in-memory computing, so obviously I believe today's GPU is too power hungry, and we need an architecture shift eventually to lower the energy consumption. And right now it is booming. We're trying to find the best architecture. Everyone wants the fastest GPU possible to train their model. That will probably continue to remain true. But in the inference space, when you are trying to use it, then everyone is trying to design their own accelerator and lower the energy. So I think that trend will continue. The design cycle is longer than these AI model can evolve. And so we also heard that we are using FPGA to try to be more agile. But I do think that in the inference space, especially in the end, the ASIC designs are going to prevail, and we'll have a more energy efficient solution to save humankind from all the energy explosion.
Yeah, I think there's we had the panel on sustainable and versus high performance yesterday, and the statistic there was 5 years ago, data centers were just under 2% of U.S. energy consumption. They are now 4%. They're projected to be somewhere between 7 and 12% by 2030. So if you look at that trend, it's one of these trends that just cannot continue forever, right? Because at some point, if all the energy goes to data centers, then that's clearly a problem. So somewhere between now and then, something has to change. But you simultaneously, in changing, you have to also deal with the kind of Jevons paradox world of, suddenly compute is lower power and freely available, so we need even more of it than we were using before. So figuring that out is, I think, an important part of what it means to be a member of humanity at this point.
I mean, you asked a philosophical question, so I'm going to give you a philosophical answer.
Yeah, that's why you're a professor, right?
So I think when I look at, particularly our students and, the incoming fresh batch of students, I think I'm less worried about AI becoming super intelligent and taking all the jobs and, eating up society and all that. I feel like we are sometimes, we trust AI more than we should. I mean, we overestimate its intelligence. And we suspend our own critical thinking in some cases, which I think is a bigger problem. So I think we need to be able to teach our next generation of engineers that too much reliant on a system which is trained on data is not necessarily the right answer. But a combination of expert knowledge, AI, which is data generated, and symbolic methods that we have been working on for a long time as a human race. I think a combination of all these techniques is what the future probably looks like. But again, you have to be open-minded, you have to adapt, you have to learn, but don't rely too much on tools. And you need to be able to make sure that your own intelligence is preserved in some form.
All right. I see another. There's a line, Mandy. So we're gonna. You've inspired more curiosity.
Thank you for wonderful discussions. I have a question. With the horizontal shift, with the horizontal shift that we have in semiconductor, we had seen a lot of trust issues with third-party service providers. Now we are trying to outsource a lot of different tasks in semiconductors with AI in terms of, design, verification, sign-off, even, creating digital twins. Do you see that trust issues are going to increase or decrease?
That's an excellent question. I think our need for trust is certainly going to increase. And as you know, you can't build a system with no trust at all. It just doesn't work. So figuring out what's changed in the world and how we're going to deal with it. I was talking to one person who said that the only way this is ever going to be fully reasonably trustworthy is if all the models are open source and all their training and every aspect of it was open source. And that's a viewpoint. Another viewpoint would be that no, eventually we will collectively come to some realization that there are certain aspects of these machines we can trust and others that are subject to easy manipulation, so we should not trust them. And essentially, that's an exercise in effort and work that we're going to have to do. There's also, we were talking about 3D-IC before. 3D-IC introduces new attack vectors onto physical systems. AI introduces new attack vectors. So we just have to figure out what those are, how we mitigate them, and, untrustworthy individuals will be with us until the end of time. So we have to figure out how to mitigate the damage they can do.
I see two more people. Do you have questions or?
Yes.
Yeah, go ahead.
Hello, I'm Sachin with Intel. I believe one of the key ways how we can tackle the energy of AI is by using emerging devices like memristors and in-memory computing, spintronic, so on and so forth. While I was in grad school, some of these research was up and coming, and I thought with the advent of AI, these would be exploding. But I don't see that, happening. So could you tell me, what is going on in that emerging devices space?
Yeah, I think it is emerging. I think the technology aspect is maturing. There are more in-memory computing, for example, using SRAM, which is very mature, and also like near DRAM computing, for example, where the technology is mature and you try to apply the architecture change first. We are working hard on the technology as well, and so and this wave of AI certainly helps. So we hope to show you something soon.
I think that there's also an interesting aspect to any form of analog compute, which is the world has been so preconditioned on digital that we are very, very conditioned to say you run the same program on the same machine over and over, or a copy of that machine, and it produces the same answer every single time. And in analog, that's not usually true, and in memristors, it's definitely not true. So that's not an insurmountable barrier, but it is a barrier. And so part of the emerging process is to figure out how to deal with that.
I believe the software ecosystem probably needs to mature, I guess, right, in order to use these kind of emerging devices with digital.
Maybe AI will help expedite that software.
Or maybe we can
development.
argue that FP4 is approximate enough anyway.
There we go.
So I'll add to that. So I think there is one aspect of it which is technological, right? So this is what we have been talking about. There is also a social aspect of it, because I feel like, when you are using ChatGPT, you're not necessarily aware of the number of joules and whatever it's spending on the cloud. So I'll give you a concrete example, an interesting anecdote, which might be a good way of wrapping up this discussion, which is we have physical maker spaces in our college, for example. Students go in, they want to solder something, wire something. At the end of the month or the week, they know how much they have spent. These many reels of wire. They know what they have wasted, essentially. So what we have also started doing is, when they are running some program in the cloud, particularly AI large programs, at the end of the month or end of the week, they also get a notification about the carbon footprint of how much they have spent. So I think this collective awareness that cloud computing is not free, although it may look like it's free, is important. I think having the society as young people in the society, kind of trying to make them understand that there is a cost associated with computing, will also make them waste less, because I think a lot of the stuff that we do is just complete wastage, right? So I think being very pragmatic about usage and where we want to use resources is going to be important.
All right, so do we have time for one more, or okay, one more question, and then we're gonna wrap it up.
So I asked this question to the guys at Siemens at a talk similar to this yesterday, but I wanted to get your guys' take on this. So the question is actually about like software tools. So you guys are talking about how AI is going to be great, and there's a lot of people who are talking about that. But one of the things that I've noticed in the semiconductor industry is a lot of you guys are using like really old, outdated tools, and really old, outdated IT infrastructure. Like a lot of you are using like VNC, you're using Notepad++, and you're using stuff that is not really compatible with a lot of these tools like Copilot and Cursor. Like Cursor's fantastic for writing TypeScript, not so great for System Verilog yet, but there's no way that any of the companies, the semiconductor companies that I've worked for, would let me use Cursor. And I've noticed that it's really behind on that front. And what's being done to bring the infrastructure, the IT infrastructure, to allow people to use these AI tools?
That's a good question. So I'll let Manoj answer that one, and then we'll call it, because we're getting dragged off the stage. But it's a good question. Go ahead, Manoj.
So I think the ROI is the answer to it, right? So if you want someone to stop using Notepad++ and VI and Emacs and move to a modern IDE and a modern hardware development environment, you have to kind of, yes, you can go take a stick and tell them thou shalt move, right? Or you provide incentives where you have code introspection, you have code generation, you have automatic testing, automatic validation. You provide all of these insights and you incentivize people to move. So I think it's a combination of carrots and sticks, but I think we have to move, right? Otherwise, a lot of the benefit that we get, you don't get to deploy en masse. So I think it is something that we all work on.
Yeah, I mean, I tried to move people towards that when I was working in the various semiconductor companies that I've been at. Not going to name names, but they wouldn't let me.
Yeah, the big companies will be a little bit slow to adopt, but they have to be more careful. They have more to lose as well. They might have more to gain, but they might have more to lose.
I'll also add that hardware people in general are skeptical of anything new. I think that's a general trend. So I think the cost of failure in hardware is so high. I think people are still sticking to VIMs. I agree with that.
Yeah.
Well, that Emacs thing, it's just not going anywhere.
Yeah.
If hardware is so hard, then why aren't we paid more than software engineers?
All right, with that, we're going to wrap up. Thank you.